Can you see my screen?
Yes, sir.
Oh, good. Okay, so we talk about the last assignment in your network lab. Okay. And this one, so we have done kind of the basics. Then we have looked at how to build the network application, very simplified one. And then we looked at a little bit into, even though we did it at user level, but little bit into what happens in the stack. Again, a very simple one compared to what actually happens, but you get a flavor that you have to run multiple threads and so on. And last assignment, actually you have an option because the time is short. So there are going to be two assignments given. You have the option to choose any one, okay, and do any one of them. And it's again a group assignment, so to be done in groups of two. One of them is about, given by Professor Mishra, so it's about a P2P file transfer thing. It is just the same thing as earlier, just more details. Okay. So again, you will have to open client server connections, file transfer, but there is a protocol. There are details to be worked out. Again, there are formats of transfer and so on. So it's going to be more details, but nothing, no new concept basically. So if you want a safe one, but just want to kind of practice more on that, you can do that. The other one that I have put up is about learning something in the middle, within the stack and the user level. So there is a type of socket called a raw socket. You may have heard about it. Okay? And a raw socket is something that allows you to kind of get a packet along with the headers at appropriate levels. You can get everything from your Ethernet, IP, TCP, UDP, every header that is possible out there, depending on the option that you choose, basically. Okay. So what I'm going to do, the P2P assignment, I'm not going to explain. You can read it. We have put it up in Moodle already. I think it's a lot of details, and you can ask questions to Professor Mishra if you want. And raw socket is what I'm going to talk about today because that is something new, basically. So what is a raw socket? As I said, it's a socket that allows you to get the data along with the headers. Okay. Now data, remember, data at any level contains the header from the higher layer as well as the data from the higher layer basically. So first of all, so opening a raw socket is the same as earlier. Only thing, to specify the option sock raw instead of sock stream, sock diagram, and so on. Sorry, this will be this socket sock raw, and then you specify a parameter which says, I said you can get headers. What headers do you want? So I can keep IP. Okay, there is no underscore here, I think. So I can say this IP proto IP, IP proto UDP, similarly TCP, or I can say raw. Okay. So when I say, okay, also I can also say ICMP, which we will use. So when I say IP proto IP, okay, what it will allow me to do is to get the packet. If I do a receive from on this socket, it will allow me to get the packet along with the IP header. Also, it will allow me to set the IP header to set specific fields in the header as I want it rather than the stack making the IP header on by default for me. Okay. Similarly, if I say IP proto UDP, it will allow me to get the UDP header, okay, as well as the data. Okay. Similarly for TCP and so on. So note that if I get the IP header plus data, I also can extract the UDP header, TCP header if it is carrying UDP data or TCP data and so on. Okay. And IP proto raw, if I remember correctly, allows, I think that is the option for it, allows you to get the complete thing right from the Ethernet. So you'll have all headers basically. All right. Okay. So the question is, what is it that you're going to do in this assignment? We'll talk about that and then I'll come back a little bit to it. So you're going to implement this command called traceroute. It's a standard command in Windows, Linux, any system based. You need root permission. Basically, to run this program. Okay, not to run traceroute. Okay, but okay, I'll come back to root permission. Sorry. So, what does traceroute do? So, traceroute, okay, if I run it, for example, if I say traceroute www.iitkgp.ac.in, it's first going to go to DNS to get the IP address corresponding to www.iitkgp.ac.in, and then it's going to tell me from my machine till the IP address for this machine here, okay, what are the intermediate routers? And it tells you something else. When I show you the assignment, I'll show you some format of it on Windows basically. Okay. Now, how does this work? Basically, what traceroute will do is this, as I said. Okay, I said this a little bit in class when we talked about ICMP. So, remember, there is this TTL field in the IP header. Okay, and when a router receives an IP packet with a certain TTL, okay, it processes the fields and then it decrements the TTL field. And if the TTL field becomes 0, then it drops the packet. Okay, and when it drops the packet, it's an IP packet that is being dropped at the IP layer. So it will send back an ICMP packet, and we have seen that ICMP packet sent back is a time exceeded packet. So if you can look up the slide for the specific type code and so on. Okay. So what traceroute does simply is this: it first sends an UDP packet, okay, with the IP header TTL equal to 1. So obviously, if I want to send the IP header TTL equal to 1, I should do something specific to do this thing, because otherwise by default the TTL will be set to some high value, typically around 30 or something. Okay, so this is my source. So source sends this packet with some random data to this, and there are, let's say, for IIT, and then here is my www.iitkgp.ac.in. Okay. So this the UDP packet will go here, it will go up to the IP layer. IP layer will find the TTL equal to 1. It will reduce the TTL by 1 to 0. It sees the TTL 0, it will drop the packet. And when it drops the packet, it sends back an ICMP. Remember, ICMP is carried, and it will put the corresponding type and code field for the time exceeded ICMP message. Okay, and when it sends back the ICMP, remember ICMP sent back with an IP header. Okay, so I come here, but there is a detail here that I will come back. Okay, so when I come here, I will know, because the source from the source IP of that, I will know the first packet, first identity of the first router on that, which is the one that it sent. Okay, then the next one, now that I know the first path, okay, I will now send something with TTL equal to 2. When I TTL equal to 2, this will forward with TTL equal to 1. Okay, this will make TTL equal to 0. This will send back the ICMP, and the IP will come back, and I will know the identity of the second router from the source IP. Okay, now I will do the same thing with TTL equal to 3, TTL equal to 4, and every time I should get back an ICMP. Note that it is not a foolproof thing. It is not a foolproof thing because ICMP is also carried in IP packet. There is also an IP packet going out. UDP is also carried in IP packet. And UDP is unreliable, IP is unreliable, so any of these packets can get lost. But typically you retry. Okay, so basically you send one, you wait for a timeout. Either you get back an ICMP within that timeout, or if you don't get back an ICMP, you send the packet again. You try three times, and if it does not come back, you say No, this one I could not find. Okay. So far so good. How traceroute will work basically? Yes, no?
Yes, sir.
Okay.
Yes, sir.
So what do I have to do? I have to send an UDP packet with the IP header TTL field equal to 1, and I have to receive an ICMP packet with the ICMP header basically. Okay. Oh, from the last slide. Okay, doesn't matter. All right. So I will need two sockets, draw sockets. One is for setting the UDP header, setting the IP header, sending the packet, and I will need an ICMP raw to receive the ICMP packet. Okay. So I will create two sockets. Call it socket DUDP equal to socket. Okay. I will say sock raw. I will say IP proto UDP. Okay. And I will create another one, socket DICMP socket. Same thing. Okay. I will say IP proto ICMP. Okay. So I'll do a send on the UDP socket, and I will set a do a receive from on the ICMP packet. Send to and receive from. Okay. Now raw sockets are raw sockets. They're supposed to send raw packets. So I don't need to bind them to anything if I don't want. Okay. So when I do a receive, for example, on the suppose I do a receive on this socket DUDP. Okay, it's going to give me all UDP packets. So I don't really need to bind anything anywhere. So what I will now need to do to send this packet, I need to create the header. Okay. So then don't worry, you don't have to do too much. So I'll create a buffer first. Think of this buffer, say, I don't know, 1024. So this buffer will actually contain, now I will have an IP header, I will have an UDP header, and I will have a UDP data. So this is what I will fill up, this is what I will fill up, this is what I will fill up. So it's kind of, you are kind of, completely making the packet yourself. Normally you just give the UDP data, the system puts the UDP header for you, then gives to the IP layer, then the IP puts the IP header for you. Is some default value for the fields, taking the IP address code, etc., what you supplied, and then sends it off to Ethernet. Okay. Now you are going to engineer all these things. Luckily for you, okay, there are two structures that are given to you. There may be a underscore here, I forgot, and struct UDP header. So look up these two structures. I'll also give you reference where to look up things basically. So struct IP header, we'll see if you look at that thing, just has the fields for the IP header. Similarly, the struct UDP header will have the fields for the UDP header. Okay. So we'll just need to fill up those fields. Now, when you fill up the UDP header field, where should you start filling it up from? Where is the UDP header here? Okay. So your first thing, basically your UDP header will start from buffer plus size of struct IP header. We are going to do a routine standard 20 by 20 byte thing basically. Okay. So this will be the first byte in your UDP header. You will initialize your struct UDP header first byte to that. So we'll have a struct UDP header star something equal to buffer plus size of struct IP header. Okay. And now that the UDP header is pointing to this byte here, you are just going to fill up the fields one by one from there. Okay. And your struct IP header starts nothing but from here. So your struct IP header star something, call it, okay, is nothing but your buffer. And then you're going to fill up your PARO, this, etc., all the fields you're going to fill. Okay. And once you have filled up the field, similarly, your UDP data is basically buffer plus size of struct IP header plus size of struct UDP header. Okay. And once you filled up the data, okay, you have got the entire IP packet ready. Some details I'm skipping here. Okay, if you have a variable sized header, then you have to do something small and so on, but let's not worry about it. You put your struct IP header, okay, initialize this, then that plus struct IP header gives you UDP header, initialize this, then that plus struct UDP header gives you the UDP data, and you start filling up the data with random bytes. So you'll fill up this with 52 bytes of random data. 52 is just a number that typically Traceroute uses for default. Okay, don't worry about it now. Are you clear how we are going to fill up this, create this packet? Again, I have not told you about the details of this or the details of this. But then if you look at this, look them up, you will just see the names of all the IP header fields in here and the names of the UDP header field. And you don't have to worry about IP options or anything. Okay, UDP header we have not done in class yet, but you can just look up. It is much simpler. It has hardly anything. It's a 12-byte header. Okay, 12. Yes, I think it's a 12-byte header, most likely. Okay, 444. Yeah, 12-byte header basically. You just have the port and nothing else. Almost nothing. Protocol and checksum. Okay. Are you with me?
Yes, sir.
Okay. And now to send this off, we will just use a send to call, just as earlier. Okay. Who are you sending to? You are sending to www.iitkgp.ac.in, whatever the IP address that you got for it. So in your Traceroute program, it will take as command line parameter a DNS name like www.iitkgp.ac.in. You will first call get host by name. You already know how to do it. Okay, to get the IP address, and then that's the IP address you will put. What's the port you should put for www.iitkgp.ac.in? What do you think?
So possibly 80 or 443.
Okay, you don't want to do that. Okay, because your goal is not to access the web server. Okay, see, all the intermediate ones are sending you an ICMP saying time exceeded. How do you know you have reached the destination? Okay, because that's going to process it. That's not going to send time exceeded. Time exceeded is sent only if it does not match the destination. Right? If it does not match the destination, it has to route further. Then it decides, should I route further or should the TTL exceeded? Okay. So you want to send it to some port, okay, which is probably nobody is running on that server. Because then when it tries to deliver to that port, when TCP tries to deliver to that port, okay, you'll find that the port is unreachable. And send you back now with destination unreachable ICMP with the port unreachable in the port field. Okay. So we have suggested some port 31768 or something like that. Okay. It's a high number. So, you know, even though it's within the registered port I discussed in class, the higher ports are probably not going to be used. So just taking a chance. Now, if you're unlucky, again, this is not a foolproof way to find the thing. If you're unlucky, it is highly possible, not highly possible. There's a non-zero probability rather that something is running on 31768 at that time. But typically nothing will be running on that web server at that time. So when it does reach the destination, you won't get a TTL exceeded anymore, time exceeded anymore. Okay, but you want the IP packet to be dropped. So an ICMP comes back telling you that the destination is reached, but something else is not there. So you want to set the port to something, so you'll get back a destination unreachable type with a code field saying port unreachable. It says why was the packet, final destination of the packet, not being able to be delivered. So port unreachable says that the destination was actually reached with respect to IP address. Now when I looked for the port, I did not find the port or anybody running in the port basically. So I cannot deliver it. So send back an ICMP, and when you get the destination unreachable ICMP, okay, you basically know that you have reached the destination. So then you print out the final thing and you stop. Is it clear? Everyone?
Yes, sir.
No. So that's about sending the UDP packet. Okay. This 52 bytes of data. Why do I need to put any data in there? I'll talk about it. Just give me a second. Okay. Now, what about receiving the ICMP? So I have this other socket, IP Proto ICMP, to receive it. So I will just do a receive from on that sock FD ICMP. Just like the same call that you have done. Okay. But raw sockets are very interesting. As I said, this will give you any ICMP that is coming back to the system. Now you may be receiving ICMP for many different reasons, because you are running traceroute, the machine is doing many other things for all you know. And there may be ICMPs for somebody may be pinging your machine. Then you will get an ICMP echo request. That will also come back. Okay, so all the ICMPs will come back. But you have the type field and the code field to find out which ones are you looking for. You are looking for only ICMPs, okay, with the type field set to time exceeded or the type field set to destination unreachable. And if the type field is set to time exceeded, the code field should be for TTL exceeded. And if the type field is destination unreachable, the code field should be port unreachable. Those are the ones you are looking for. All right. So when you do this, what this will give you, it will give you the packet, okay, with the ICMP header. Okay, and then the rest of the thing. Okay. And what ICMP does, this is probably something I did not mention very well in class, is when it drops the packet, it puts the first, I think, 64 bytes of data, the packet that it dropped, into the thing, into the ICMP packet. Okay. So now you got the ICMP header. So when this receive from will just block for an ICMP, when you get the ICMP header back, then when it comes back from the block, suppose it's an ICMP, okay. Well, not suppose, it will be an ICMP, or there's a timeout possibility. Gets the ICMP, you know the header format. Again, you can start from here, and there is again a struct ICMP header thing. Okay, so you can just read this into that struct ICMP header, and then look at the fields of that header to see that what is the type field, what is the code field. And if the type and code matches, then you can take appropriate action. Only thing is that, as I said, every ICMP will come back to you. So you need to look at the type and code and kind of reject all other ICMPs that are coming. So go back and wait for the ICMP again. With me?
Yes, sir.
Okay. So the other thing that is there is, now you see, suppose you send something and this came back with the TTL exceeded. Okay. But now suppose there is some other application which was sending something, okay, a valid application, standard application that is there, And for some reason, because of routing loops or something, there was one packet of it that it sent also got dropped at some other router somewhere. Okay. And that also came back with TTL exhibit, time exhibit. So there can be other reasons other than your traced out packets for an ICMP packet to be received with time exhibit or destination unreachable. Okay. So how will you distinguish if, for example, if a time exceeded ICMP comes back, how will you distinguish whether this is in response to the packet that you sent out in your trace route, or this is for some other application packet that has been sent out from this machine? What do you think?
And maybe we use those 64 bytes of data to signal.
Yes, you use that byte of database. Okay. So when it puts in, it puts the IP header in there. Okay, and the data out there. I'll confirm to you the exact number of bytes it sends back. Okay. But you're correct, absolutely right. I can kind of match what I sent to who I sent, okay, with what is coming back. So whenever an ICMP packet, sorry, an IP packet is dropped and ICMP comes back, what happens is you will get an ICMP header, okay, and you will get a data. Now this thing varies from type to type a little bit, but typically the first, I think I remember, as far as I remember, 64 bytes of the IP packet that is dropped. Okay, that will be put in here. Okay, now that's where the 52 comes in. So you send an IP packet. What did it had? It had an IP header, it has an UDP header, and then has an UDP data. Okay, I think it's 64 on. So when this gets dropped, out of this data, the first 64 bytes are put in here. What are those 64 bytes? There's a 12 byte UDP and a 52 byte data. So when you get back the ICMP, the 64 byte here, and then there will be IP packet put on top of this, and then this will be sent back. Okay. Now you have got on your raw socket from this part. This is stripped off because you have said IP proto ICMP. If you have said IP proto IP, the IP header would have been there also. You done receive. Okay, but then there will be too many IP packets. You don't want them. You want only the IP packets that are carrying ICMP data. Okay. So I do IP proto ICMP. Okay. And now I have the data, and now I can match it with the UDP header that I sent, and I can match. Basically, I know the 12 byte UDP header, and I can match with the data that I sent with the data that is here to identify whether it is my packet or not. Okay. I'll confirm this, but I think it's 64 because that's where the 12 and 52 comes from. That this strange number 52 comes from. But you can match that database. So you can put some RB random byte so that it does not collide with anybody or with very low, with very high probability. Okay. And when it comes back, you just have the data in a buffer. You just match it with these 52 bytes. And this is just a buffer that you have got at the end of receive. Okay. You just take out the appropriate part of the, because you know the size of the ICMP header also. So buffers beginning plus size of struct ICMP header will give you the beginning of the data, plus UTP header will give you the beginning of these 52 bytes, match these 52 bytes with whatever you have sent. If they are the same, process the packet further. If they are not the same, this time exceeded for something else. With me? Yes, no, please.
Yes, sir.
Yes.
Okay. So that's all you have to do, but let's now look at the assignment. Close the assignment. Just give it a second. Why is it so slow? Okay. Okay. So here is a trace route from my machine to www.itkgp.com. So on a Windows, it will show you this less than 1 millisecond, less than 1 millisecond, and so on. If you run it on a Linux machine, it will actually show you 0.371 millisecond and so on. So when I run trace route www.itkgp.ac.in, it first does a DNS lookup to get this 10.300.102, and then it will just find the fifth one. It has found. Now this is a local network. Well, not exactly LAN basically, but within IIT, so there's not much loss and so on. So trace route is not, because this basically IP packets. Okay, so they can get lost for many reasons. So it's not a foolproof thing. Okay. Okay. What do you have to do? As I said, you have to run this like you have to create a function called mytraceroute, sorry, program called mytraceroute.c, compile it, and this should run like this. I will run mytraceroute www.itkgp. You create two raw sockets, S1 to send UDP packets and S2 to receive ICMP packet. Okay. So this part is simple. Now, so first you find out the IP address of www.itkgp. Okay. Then you create the two raw sockets. That's also okay. Now this is something that I have not yet told you. Now, if I create, okay, I'll come back to this. Give me a second. I should have told you this earlier. But okay, let's just look at the one. Ignore 3 for the time. 4 is you want to send the UDP packet using that IP proto UDP socket. You set the variable, have a variable detail equal to 1. You create a UDP datagram with payload size 52 bytes, random bytes. Okay, but you need to follow the exact format of UDP header. But it's easy, as I said. There's already a struct UDP header that is given to you. Set the destination okay, 32.164. I said not 768. Okay. Anything you use a high number basically, right? So that you know your chance of getting a destination unreachable message is very high. Then you append the IP header, as I said, set the fields of the IP header, and the TTL field you set to the variable TTL. So initially, the first one will go with TTL equal to 1. Okay. Now you make a select call to wait on the other raw socket, the ICMP socket. It's waiting to get either an ICMP or if the IP packet is lost or something, a timeout value of 1 second. Okay. See, the select call comes out with a receive of an ICMP. There are 3 possibilities. Either it is an ICMP destination unreachable, and you can check basically. I think this is something wrong. This has to be the type field to be equal to 1. So I'll modify this. Okay. No, wait a second. Oh, the protocol field is IP. Okay, so it has been with a fit for an ICMP packet. I don't know why we need to check the protocol field. I'll check why I check that. Okay, I don't think you need to check that. So because because you have a raw socket with ICMP, it will only come back with ICMP. So you can directly check the type field and the code field. Okay. So the type field is there. You have reached the destination, received the response from there. To be safe, check that the source IP, its destination matches with your target server IP address. Okay. Train nicely, okay, and exit after closing the sockets. I will check this slightly. Okay, this is not the way to check. Okay, I'll check. Otherwise, it's time exceeded, so check the type and code field. Okay. If you have received any other ICMP, it's a spurious drop. Go back to wait on the select call, but then wait with the remaining value of time. Because your original ICMP was supposed to come back with 1 second. Okay, it has not. All right. So you should, if it comes your spurious ICMP in between, you should wait for the remaining value of the time. And for each ICMP, you calculate the response time. So now you know how to set timers and all. So every time you set an ICMP, you set a timer. If you get a response, Look at that timer and then you just, for each TTL you will only send 3 values, so you know what they are basically. And you can match the random bytes to make sure that you have received the correct ICMP. And then you print them, just the hop count, that is basically the TTL value, the IP address of the router, the response time. Okay. And if the select call times out, then you repeat from step 4 again. Okay. So your first IP, there was no ICMP received. So send with the same TTL same again, see if it receives. You just need to get one of them. So 1 out of 3 is fine. If you don't get back anything, just print this star, 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 star. Okay, which means for that second hop, I could not find the route. But then I will try with the third. So increment the variable value equal to 1 again, continue with this. Okay. And as I said, there's a possibility that everything gets lost or the destination unreachable does not come back. So you don't know how long to go for. Okay. So you stop at TTL equal to 16. 16, I just said normally you stop at much larger, but 16 we just said because we are going to do internally, so 16 is never going to get used. Okay. This is one thing I want you to note. When I set the IP header, I said you have to go to the struct IP header and set every field separately. Now, the only field I really wanted to set was the TTL. And there is an easier way, okay, to set the TTL field without having to set all the IP headers. You may find that out. I'm not going to tell you. But for this assignment, I don't want you to do that. I want you to fill up each and every IP header field because they'll give you practice, make you remember the IP header fields and so on. Okay. But in practice now, for many of the IP header fields, there's an easier way to, it's a function that you can call, okay, to fill up the field rather than actually having saying that this dot this equal to this and so on. Okay. So this part, wait for me for 1 day, this A and B, okay. I'll rewrite them more clearly. Okay. It's there, everything is there, but I'll rewrite them more clearly with the code and type field. So, okay. Okay, any questions so far? Okay, if not, I'll explain this business about that IP header input. I should have said that earlier. So you see, you are doing a send to, okay, on an IP proto UDP option raw socket. Okay, so this is what by default this tells the system that you want a raw socket at the UDP layer, which means when you receive from it, you want the UDP header, okay, but not anything else, not the IP header or anything. Okay, and when you send to on it, you will give me the UDP header. So the system does not have to put up the UDP header. Okay, but by default, because it's UDP, that will happen only for UDP headers. So if you don't say anything else, okay, the system will also put in the IP header itself. But you want to put in the IP header here yourself. Okay, so this is the alternate way I was saying. Okay, that by default you can allow the system to put in the IP header, but then you can say in that IP header that you put in, this one field I want it to be always this. Okay, so I encourage you to find how you do that. Okay, it's easy, but then I don't want you to do that for this assignment because we want to kind of have a feel of setting the UDP header, IP header yourself. Please. Okay, so what you do is there's a function called we'll do more in the next class. You can set some options on a socket that you have created. So this on this socket FD UDP socket, you will say, and these options will vary. I may forget the exact order of things a little bit. Okay, IP proto IP, and then IP header include. I think you put it in a variable and then you pass the variable and the length of that basically. Okay, not directly like this basically. So I think that is true. I think you pass a something, call it IP header include equal to IP header include, and then you pass ampersand. Handwriting today is terrible, but you get the idea, size of that. But you can look up the syntax. So what you are saying is, for this socket, for this layer, okay, whenever I do a send on this socket, I will supply the IP header. Okay. So the system will not put the default IP header for you. If you do not do this, okay, then the system will overwrite your IP header because it thinks that it has to put the IP header. It has, you have just or not, yeah, it will just give you an IP, right? So one more step that you have to do after creating these sockets, on the UDP socket, you have to set this IP proto IP, set this IP header include flag, okay, which basically tells the system, even though it's a raw UDP socket, when I do a send to on this raw UDP socket, I will have already put in the IP header. So the buffer that I send you, just give it directly to Ethernet. Is it clear? Yes, no?
Yes.
Yes.
Okay. Yeah. Okay. And the other couple of things when you implement it, that you will have, to do basically, one is that when you fill up the IP header, you have to fill up the IP checksum. IP checksum, there is standard codes available, so you can borrow them. You know, the checksum method is the same method as we have done in class for when we did this checksum, CRC, all those error detection things. Okay. The same method, but the standard method, standard codes for available for IP checksum calculation, and do that. The other thing that you have to do is that a UDP also has a checksum, same as TCP, and it also does the exact same pseudo header thing that we discussed in TCP. So computing the UDP header, you have to first create that pseudo header, put the entire buffer from UDP header and data after that, and then do a complete thing of that. But you have all the values, so it's just a concatenating thing one after the other. And then you apply the same checksum algorithm on that buffer basically. So I think you can figure out those details. There's not much work. Now, regarding where to study from, this is an old book, but this is a Bible of network programming, as well as standard OS programming. So you can look up Unix Network Programming Volume 1 by Richard Stevens. Okay, there's a chapter on raw sockets. There's a part on trace route also there. I request you not to read that. Or okay, go ahead and read that if you want to understand, but then write your own code completely after. You just understand raw sockets from there, and then go ahead and write your own code. Okay. So this is one book, the standard book that I follow also. But then if you just start with raw sockets, IP proto UDP, in different places it is there. So I'll just give you one reference. If you want, even tutorial on raw sockets, whatever. And those may be good to read one, because we are doing only UDP and ICMP, but the idea is very simple. Again, as I said, if you do IP proto IP, it will give you, when you receive from it, it will give you IP header and everything, IP payload. And when you send, you're supposed to create the IP. When you do IP proto TCP, okay, when you receive from, it will give you the TCP header and the TCP data. When you send, you're supposed to create the TCP header, put the TCP data in. Same for UDP, same for ICMP. And whatever you have not specified, unless you have specified the IP header include flag, then IP will put its own IP header on top of it. So if you want also to specify the IP header along with a TCP, UDP, ICMP packet, okay, you have to set that flag on that socket. I would not say flat, set that option on that socket. Okay. In the next class, we'll do more about sets of option and some other things regarding sockets. So that's it. So your choice once again, whether you want to do the same old thing, but it's safer. You know how to do things. Okay. But it's a lot more details, so you have to think about it. Take a look at that. Read both of the assignments. And this one, you got the idea. Even the version that I have out there is okay. It's only there's some details. Is only when you start coding you will realize that there may be some ambiguity there. So those I will correct very soon. Very soon. Okay. And deadline for this is March 30th. So I don't think we'll extend it much. 1-2 days maybe, because we need to give the TAs enough time to create and so on. And you will have one more lab test. I'll discuss with the other teacher and let you know. That will probably be on either 28th, the Monday on that, or on 5th, most likely 4th, most likely on 4th, because now we have the theory class on 28th. We don't have enough time for a lab test basis, but we'll see. The exact details we'll tell you this. And 4th, everybody should be here, so we may also have an offline lab test. Nothing sure, don't worry about it. We'll see. We understand, even if we have offline, we understand that it's not possible to remember all the syntax and everything. So most likely not. But anyway, the date probably is going to be 4th March as of now. Okay, I'm done. So if you have any questions, ask me. So regarding the assignments for the P2P assignment, if you have any questions, please ask Professor Mistro, send him mail. If you have any questions about raw socket one, ask me. Okay, so if you have any questions, let me know. Otherwise, class is dismissed. You can leave.